To complete the initial algebra steps for logarithmic differentiation, first we rewrite the function f of x as y equals, and we see that this function has a square root in it, and so we want to go ahead and rewrite that square root as the 1/2 power. But there's nothing else that needs to be altered before we begin. Okay. So once we have the function rewritten, we take the natural log of both sides. So we have the natural log of y on the left, and then we have the natural log of this fraction on the right. So we've got x cubed on the top times x squared plus 4 raised to the 1/2 power on the top still. And then on the bottom we have 3 to the x and the factor x plus 1 raised to the 5th power. So the whole purpose of introducing the logarithm is so that we can start doing algebra to be able to change quotients into differences and products into sums. The one other thing that we can do is change powers into constant multiples. And so all of those sorts of things that we're trying to change them into are easier types of functions for derivatives, and that's our whole goal. This is a complicated function right now for the derivative. Algebra makes it a little bit simpler. So the algebra step that we would need to do first here is we have the natural log of a fraction. So the first thing we're going to be doing is changing division to subtraction. And so we have the natural log of y on the left-hand side is equal to the natural log of the top. So the top there is x cubed times x squared plus 4 raised to the 1/2 power. Minus, so that division bar then becomes a subtraction. So we subtract then the logarithm of the bottom. So it would be 3 to the x times x plus 1 to the 5th in the natural log. Okay. So now that we've gotten rid of the fraction, what we notice is within each logarithm on the right-hand side, it's a product of two things. And so we can split up those products to sums. And so what we can do then is we would have natural log of y on the left still, and we'd have natural log of the first term in the product, which is x cubed, plus the natural log of the second term in the product, which is x squared plus 4 to the 1/2. Now we need to subtract, but remember what's going to follow the subtraction sign now is going to be two terms that are added together, because the product of the inside of the logarithm is going to become the sum of two different logarithms. So we need this grouping symbol here. And so it would be subtract the natural log of 3 to the x, that's the first term in the product, and we would add to it the natural log of the second term in the product, which is x plus 1 to the 5th. And we close those grouping symbols. So to continue our work, we have exactly where we left off here. The next thing we need to do is distribute. We have that subtraction sign there within the grouping symbol, so let's go ahead and distribute that out. So we have natural log of y equals natural log of x cubed plus natural log of the factor x squared plus 4 to the 1/2 power. And then we've got the subtraction that we are distributing. So it's minus natural log of 3 to the x minus natural log of x plus 1 to the 5th. And then the final algebraic step that we can do is we've got powers in these different terms, and those powers can be brought down front as constant multiples, or just multiples actually. So we have power here, powers to multiples. All right, so we've got natural log of y is equal to, so the first term is natural log of x to the third. So the third power we just bring down front, and it would be natural log of x times that. And it's really important to notice that this is still algebra. This is not a derivative. It's not a power rule of any sort. We're just algebraically bringing down the exponent in front of a logarithm using a property of logarithms. And we do this for each term. The next one, the power is the 1/2 that we have, so we bring it down front, and we're left with the natural log of the x squared plus 4. The next one is where I needed to correct myself. It's not always constant multiples. Here we have that the exponent is x, but we can bring down the x in front and have it be times the natural log of 3. And remember, the natural log of 3 is just a constant itself, so we've got x times the number natural log of 3. And then in the last term, we have the power 5 that we bring down, and it'd be times the natural log of x plus 1. So at this point, you'd be ready in calculus to take the derivative. But you may ask yourself, well, there was a whole lot of time and a whole lot of effort and a lot of copying and a lot of steps to get this far, and I haven't even done calculus yet. Is this really better? Well, think back to what our original function is. It's here at the top of the page. That original function would involve a quotient rule, and within that quotient rule, we would have two product rules, one for the top when we take the derivative, one for the bottom when we take the derivative. And within those product rules, we would have a chain rule, plus a special derivative for the derivative of 3 to the x. And so that's a pretty involved nested problem, whereas here, sure, it's a lot of steps, but it's algebraic steps. And then you'll see in calculus the derivatives are fairly easy from this point. The other thing I wanted to point out is with practice on these, I anticipate that you would be able to get to the last step or almost the last step all at once you've seen really what's happening. Because the two terms here, the first two terms, the two that come with the plus sign, those are coming from the factors that were on the top, the x cubed factor and the square root factor. Those are coming from the top factors. Notice the two that have the subtraction sign, the last two then. Those two that have the subtraction sign come from the bottom two factors, the 3 to the x and the fifth power factor. And so you'll see right away then that all factors that come from the top come with a plus sign, all factors that come from the bottom come with a minus sign when you split it up into sums and differences. The other thing to notice is that last step that we did was bring down the powers to multiples, so all those exponents that you see in the original function end up just being the multiples in the front of the logarithm for each term. So my guess is with some practice, you'll be able to not have to write 2 pages worth of work in algebra just to get to the point of taking the derivative. You'll get good enough at this so that you'll be able to write the end step at the very beginning.